Lesson 1 is Introduction to Functions, and in 1.1 we're going to talk all about what a function is. So starting up at the top, a function is a relation between two sets of values where each input value has exactly one output value. And that might not mean a whole lot yet, but we're going to go through a few examples to kind of see exactly what that definition is talking about. One little note I'm going to add on the right side over here is that it's okay for multiple inputs to share an output. And again, it doesn't have to mean a lot right now, but write it down so it's something that you can refer back to after we go through these examples. So all three of these right here are different sets of functions. And there's just kind of like certain rules that functions have to follow in order to be like classified as a function rather than just the more general term a relation, which is just like kind of showing the relationship between two sets of values. So one of the best examples of a function in like kind of a real life situation is birthdays. So if we think about a birthday function, whenever we organize functions in like a table or a mapping, we'll talk about what that means in a sec, we usually put the input values on the left side and the output values on the right side. And a function is kind of like a machine, like you put something in and you get something out. So when it comes to the birthday function, the input is going to be the person. So the person, whatever their name is, and then the output is going to be their actual birthday. So this example says, Joe's birthday is March 20th, Mary's birthday is June 4th, Drew's birthday is January 16th, and Allie's birthday is March 20th. So I'm going to go back up to the definition and that kind of note. So it says a function is a relation between two sets of values where each input has exactly one output. So what that means in the context of our birthday function is that each input, so say we look at Joe, only has one output, meaning Joe only has one birthday. He doesn't have more than one birthday. That would be impossible. He can't have more than one birthday. And then the note over here where it says it's okay for multiple inputs to share an output. So like how Joe and Allie both have the same birthday, they have the same output. That's okay for two different people to have the same birthday. That happens in real life. What's not okay is for one person to have more than one birthday. In this case, it would be like Joe having more than one birthday, the input of Joe having more than one output. Okay, we're going to get a bunch more practice with these though. Okay, so moving on to this middle section right here. So on the left, that was a table. This is an example of a mapping. So where there's like kind of these two oval type shapes and you have the input values on the left and they're like arrows pointing to the output values on the right. That's called a mapping. So on this mapping or this function, we have a list of students in our input bubble, and in our output bubble, it's pointing to their favorite color. So if we kind of follow the arrow from each student only has one favorite color. I know kind of in real life you could maybe have more than one, but in this case, let's say you just have to pick your very favorite. So the input, Maria, has this one favorite color, green. The input, Devin, also has one favorite color, green. And then Amelia has that one favorite color, blue. So each input, each student only has one favorite color, one output. So that makes it a function. And then we're going to move over to the set of points over here. So you can also write a function just as a set of points and you'll see them written that way. When you see it, the first number, usually like what is in the spot of the x coordinate, is your input, and the second number is your output, the y coordinate. So in order to check for like if a set of points is a function or not, you just want to make sure that there's not one input that goes to two different output values. So like right here, we have a 2 that goes, or negative 2 that goes to 8. Right here, we have a 4, it goes to 10, 1 goes to 7, negative 9 goes to 3, and 7 goes to negative 4. So there's no repeat input values. And in fact, all of the input values are completely different. Negative 2, 4, 1, negative 9, and 7. So that means that we can't have one input that's going to two different outputs because we don't even have an input that's repeated. Okay, so moving down to some counter examples because sometimes that helps it make even more sense. So these are non-functions down here. So I'm going to look at the mapping in the middle, this one right here. And this is an example that has the input of the student in the like kind of input bubble. And then the output is what pets they have. So for example, Maria has a cat, and then she also has a bird. So that one input, Maria, she's the input, she has two different outputs. She has a cat and a bird. So that breaks this rule right here where it says each input value has exactly one output value. It breaks that right away. So that would mean it's not a function. It would just be called a relation, which is kind of like a more general term, and it doesn't have as many rules around it. And then if we look at like Devin as our input value, so Devin right here, they have the dog, and so that's okay. And then Amelia has just the cat, so that's okay too. But the fact that Maria has two different pets, Maria is one input, and she goes to two different outputs, so that means it's not a function. That would be like Maria having two different birthdays if we use the birthday example. And then for the set of points over here, so remember input is the first number, the x coordinate, and then the output will be the second number, the y coordinate. So right here we have like a -3 that goes to 9, -2 goes to 11, 4 goes to 12, -3 goes to 6, and 5 goes to -10. So if the input values are all the first number in each set of parentheses, this point right here, these 2 points, -3,9 and -3,6, those cause a problem because this is the same input, -3. One time it goes to 9, and one time -3 goes to 6. So that one input, -3, has two different outputs. One output is 9, one output is -6, and that means it's not a function. Okay, so moving down to 1.2, this is functions and tables, which is one of the more common ways that you'll see them written. So example 1, determine if the following tables represent functions. So in order to determine if they represent functions or not, we just kind of need to see if, I'm going to scroll up to the top, if it breaks this rule that each input value has exactly one output value. So one of the kind of like tricks that you can use when you're looking at a table is just see if you have any input values that are repeated. So if we look at A, the input values are -4, -1, -1, and 0. So that -1 is repeated, so it potentially is going to two different output values, and it is. -1 is going to 9, and it's also going to 5. So that one input, -1, even though it's like written twice, it still counts as the same input. That one input, -1, is going to two different outputs, -9 and, +9, and +5. So because that one input goes to two different outputs, we would say no, not a function. And then for example 1b, we have our table, we have -4 that goes to -4, we have -2 that goes to -2, 0 goes to 0, and 2 goes to 2. So the input and output don't change necessarily, like each number is going to the same one. That's not a problem at all. The only problem that happens when you're trying to find a function is if you have the same input value going to two different output values, just like we did right here where we had the same input, -1, going to two different outputs, a 9 and a 5. But in that second table for B, we honestly don't even have any repeated input values because they're all different numbers, -4, -2, 0, and 2. So that means that each input must only have one output, so that one would be a function. So yes, this one's a function. Even though it was kind of funky that they all went to the same number, that's okay. There's really only that one rule that you have to look out for that kind of talks about how each input can only go to one output. Okay, so moving down to 1C, this is our last table. Oops, sorry. So this is a table for a specific equation, and we're given that equation. It's y equals 4x plus 6. So on the left side is our input, which is x. Most of the time it'll be x as well. Sometimes it could change a little bit. And our output is y. So same thing applies here. We just have to make sure that each input only goes to one output. So -2 goes to -2, -1 goes to +2, 0 goes to 6, 1 goes to 10, and 2 goes to 14. So all of our input values in this table are different, -2, -1, 0, 1, and 2. So we don't have any one input value repeated, but going to a different output value on that repeat number. So this is okay, it doesn't break that rule. This one is fine. So yes, this one would be a function. So before we go on to example 2, I'm going to kind of zoom out and just summarize kind of like a trick that you can look for when you're deciding if a table is a function or not. And this only really applies for like I don't want to say it only, but the main thing I can think of where it applies is a table. It wouldn't work for a mapping. So when you have a table, each like kind of x value or input value lines up with an output value like it does here, like -4 to 12 and -1 to 9. So when you're determining if something is a function or not a function from a table, the main thing you want to look for is if you have an input value that is repeated, because that's the like kind of set up for potentially breaking the rule, is seeing the same input number twice and then seeing it go to two different numbers. So up here it went to the 9 and down here it went to the 5, even though it was the same input. The rest of the tables had all different input values, like this is -4, -2, 0, 2. Those are all different numbers. So it's really not possible for this table to even break the rule because we don't see the same number repeated. And then same thing here, -2, -1, 0, 1, and 2. We don't see the input value repeated, so there's no like real setup for it to break the rule. Okay, so main thing to look for in 1.2 is if you see a table that has the same number twice in the input. It only breaks the rule if it does in fact go to two different numbers. If for whatever reason you had the same number repeated on the output, that would be okay. Okay, so example 2 now. So determine if the set of points represent a function. So it can be pretty tricky, at least like with my eye, to like determine the list of points is a function or not. But you can always take that list and you can rewrite it as a table if it makes it easier for you. So I'll show you without making a table first, and I'll show you making a table second. So if I am not making a table, I'm looking at all of my input values, -2, and remember, sorry, let me go back. If you have a point, the first number is the input, and the second number is the output. So my input values are the first number in each point, -2, -1, 0, 1, and 2. And then my outputs are the second number. So -2, 2, 6, 10, and 14. So you can use the same trick here as we did with the table and see if you have any input numbers that are repeated. So -2, -1, 0, 1, and 2, and none of those are repeated. So the same thing works here. If they're not repeated, then each input must only have one output. So that would mean that yes, it's a function. But if you're just more of like kind of a visual, like I like seeing the numbers line up, take the extra time and to just make the table, it's worth it. So yes, this would be a function, and then I'm going to show you how to set up the table. So draw the vertical line, and then we'll make two columns, and the left side will be the input, and the right side will be the output, and that's always how these tables are organized, is input on the left and output on the right. And the input is going to be the x, and the output is going to be the y. So then I'll take each of and I'm going to go point by point. So let's say I'm going to take this point first. So my input is -2. My output is -2 as well, because it's -2, -2. And then I'm going to move to this point, -1, +2. And then this point, 0, 6. And notice the points were organized kind of the same way as the table, like 0 was on the left and 6 was on the right. 110, and then 214. So if it's easier for you to kind of tell from the table, like, and look through each individual output and recognize that yes, each input has just one output, so -2 only goes to -2. -1 only goes to 2, 0 only goes to 6, 1 only goes to 10, and 2 only goes to 14. You can draw the table as well to confirm that it is a function. And then this happens to actually be the same exact table as over here, but it was just the original problem was written a little bit differently, so it's really important to be able to recognize kind of the different structures of these problems. So yes, for example, 2, that one is a function as well, and then like I said, you can kind of decide what works best for you, whether it's leaving it as the points or turning it into a table. Okay, so 1.3 is functions and graphs, which a lot of times when we see graphs, it's like, oh, terrible. But deciding if a graph is a function can actually be kind of fun. So it's in order to determine if a graph is a function or not, you use something called the vertical line test. So with the first bullet point starting there, it says a relation is a function if there are no vertical lines that can be drawn that intersect the graph more than once. And then the second bullet point, a relation is not a function if there is at least one vertical line that intersects the graph 2 or more times. So what that means, and I'm going to show you a couple examples of each. We'll zoom in on this one. So this is an example of a function because you can see there's a bunch of vertical lines drawn on here. And like you could technically draw it anywhere. I'm actually going to maybe see if I could like slide it around. So I have this vertical line, and if I drag it anywhere along the graph, it only ever intersects the graph, which is the blue part of the line, in one point. So if I can do that anywhere along the graph and it only intersects at one point, that means that yes, it's a function. So it passes the vertical line test. And I'm going to leave a little note. You may see me shorten, like if I need to write vertical line test, as VLT. So vertical line test, if you see that. Okay, and then I'm going to zoom in on this second one. So here we have vertical line as well. So I'm just going to start one right here and then drag it over. And then you can see there's like a ton of spots if I drag my vertical line through the graph that it's intersecting at more than one point. So that's what makes it fail the vertical line test, if there is kind of more than one intersection point between your vertical line and the graph itself, the blue kind of like curved line on here. And then same thing, I can keep dragging it through and it just continues to intersect at more than one point. So it just keeps breaking that test, and that means that it's not a function. And then the last one, so if I draw my vertical line, I'm just going to start it here, and if I drag it over, so it's okay right here, it only intersects like that one point. That's fine, that doesn't break the rule. But if I drag it right here, and so it can be anywhere on the graph, if it breaks the rule at any point on the graph, it means that it's not a function. So if I put my vertical line right there, it hits at that point and at that point. And I know this graph looks kind of crazy because we haven't learned this yet, but these graphs do exist where they're kind of like broken apart. But the big point is that if your vertical line crosses through the graph, the function, at 2 or more points anywhere on the graph, it breaks the rule, it breaks the test, and that means it's not a function. Okay, so moving down to this example, determine if each graph represents a function. So for 1a, I'm going to zoom way in. You can see it's like this kind of crazy curved graph. I'm just going to draw my line here, and then we'll start to drag it through. So I can keep dragging it along to the right, and you can see it's only ever crossing at one point. It never intersects at more than one point at once. And then continuing on, and it's still only ever crossing through like right there at that point. And that stays, this isn't gonna like keep going with it, unfortunately. Like, let's see, yeah, it stayed kind of high. But anyways, it only ever crosses at one point. So if I draw my vertical line right there, it's crossing at that point. If I draw my vertical line right here, it's crossing at this point. Anywhere along the graph, it's never crossing at more than one point. So like just right there, just that one intersection point. In order for it to break the vertical line test, you would have to have another intersection point somewhere along that one vertical line. So say like right here, which it doesn't cross there, or right here, it doesn't cross there, or up here and it doesn't. So this passes the test. So we would say, yes, it's a function. And you can even go one step further and say it passes the vertical line test. And I've also heard this like vertical line test referred to as the pencil test. So the reason it's called the pencil test is because you could hold up a pencil or a pen for that matter as your vertical line. So if you were to like hold the pencil up against the screen and just drag it along the graph and see if it intersects your graph at more than one point. Okay, and then moving over to example 1b, and then this is the last example from this set of notes. So if I set up my vertical line and then I start to drag it through, you can see it starts to intersect more than once right there, and it could be anywhere in this section that we use as kind of like our reference point. So like right here, it crosses right there and right there at the same time on that vertical line. Or if I put my vertical line right there, there's actually like 3 intersection points. So it crosses through 3 times, definitely fails the vertical line test. But you get the point. If there's any possible vertical line that you put on your graph and there's more than one intersection point with the like graph itself, that means it fails the vertical line test and it would not be a function. So this one would fail. We'd say no, not a function. And then we could go one step further and say it fails the vertical line test. Okay, so just want to recap really quick. So 1.3 was using the vertical line test to determine if a graph is a function or not. And then 1.2, that was identifying if a table was a function or not. And in order to do that, you want to look for any set of input values that may be repeated that goes to different output values. And then 1.1 was just definitions of the function itself. If you don't have this written down, you do want to save it and kind of be able to refer back to it later, and this note as well.